Uh, Hello, everyone. Welcome to the second half of morning session. This session is still on TSN. I'm Takumi Nomura from Honda, and I'm also a moderator of this session. We have still 3 presentations by lunchtime. Each presentation must be within 30 minutes, including Q&A and discussions. For audience, just as a reminder, please mute your phone before we start. Please mute your phone before we start. The next presentation is Layer 2 Security for Precision Time Protocol Frames for Automotive Ethernet. I'd like to welcome the speakers to the stage. From Cadence, Mr. Shubham Agarwal and Mr. Krunal Patel.
Hello. Yeah. A few months back, I was watching a movie. The movie name was The Fate of the Furious. It's a famous franchisee of the Fast and the Furious movie. There was a scene where a villain and her team of hackers uh, they are hidden in some undisclosed location and remotely controlling the hundreds of cars and doing some nice cinematic stunts by the controlling the brakes and acceleration and changing the navigation of those cars, right? So after that I was seeing that there were few discussions floating over the internet forum if this case is possible in real life. So my answer is both yes and no. So theoretically it is yes, but I would say no. Why? Then I will give the credit to this community, right? We make sure that this type of things doesn't happen. We take the extra efforts. We add the security measurement to avoid this kind of situation. And today we are going to discuss one such security protocol. The protocol is the MACsec, and the MACsec is the layer 2 security protocol, which will also include, we will also include the precision time protocol frames. So overall, our presentation will be around PTP or MACsec. Hello everyone, I'm Krunal Patel, and I'm a product engineer from Cadence Design System, and with me is Shubham Agarwal. He is the R&D manager of the Ethernet verification IP team. Thank you. And so, okay. Sorry. Okay. So, before discussing this security protocol, we will give you the brief idea of the time synchronization and the time synchronization in the automotive and the precision time protocol. Then we will discuss the common security threats for the automotive Ethernet network, and then I will give you some brief introduction of the MACsec protocol and the frame format and all. And we will see why the PTP or MACsec is required in automotive Ethernet. And we will see, I will explain the each functionality of the MACsec using a use case. And then we will come to the most important part, which is the functional verification challenges for the PTP or MACsec IP, and we will also discuss the solution for each problems. Yeah, thank you. Okay. Uh, so at a particular time, the automotive industry has continued to add more and more sensors and electronic control units, which we say ECUs, right? And the today's vehicles are packed with the advanced driver assistance system, which is ADAS, and the cameras and the radar sensors and infotainment sensors and telematics and rear view and front cameras and driver monitors, right? We also have the brake assistance in the vehicle. So as we see, the most, or we can say all of these applications are time critical and mission critical and time sensitive, right? And the deterministic latency between the each node are expected from the network, right? And the all these sensors and actuators are used to connect. In a few years back, it was used to connect through this protocol like CAN or FlexRay or lane buses. But after the introduction of IVN in vehicle network, the industry has started adopting the uh, Ethernet network. So I think that this synchronization. So still we see the vehicle where both of these protocols or both or the multiple protocols being used in the network, like Ethernet and the plus CAN or some other, right? So the synchronization is not only essential within the Ethernet network, but it should be also synchronized between the other physical systems, right? Okay, so let me give you some little bit overview of the PTP. Um, so in an automotive Ethernet networks, it contains the multiple nodes and require the synchronization between various nodes, and it is not just the instrumental, but it is also a highly complex process, and it will become even more and more tricky when we synchronize the clock between the master and the slave, right? Because as we know that in real time, the some of the nodes would act as a master while some will be the slave. Okay, so we must make the communication process smooth, and for that the local clock of these nodes must be synchronized. So problem with this synchronization is that we have clock running the master as well as in the slave. So if we make the master's clock to synchronous to slave, then synchronization doesn't happen, since we know that there will be a propagation delay of these messages as well as the propagation delay of the electronic circuits of the master and the slaves, right? Okay, so but the good thing is that these electronic circuits propagation delays are not random. In most of the cases, these are the it will remain constant, so that we can predict it and they match and time offset these delays, right? So to do this, IEEE has introduced a protocol which is a precision time protocol, and for automotive, we generally use the generalized precision time protocol, which is GPTP. Okay, and okay, so let me explain a little bit of this how this protocol works. So to synchronize the clock, a sync message being sent by the master, and which timestamp the receiving time of the same, and just after that the master sends the follow-up message, which also which timestamp which had the value of the time when the sync message was sent. Okay, and in return the slave will reply with the p delay request. Okay, so that's how the slave will find out the difference between the two values and add it to its current value, And after this, the time difference between master and slave narrows down to only the propagation delay of the message. And to overcome this, the slave will send the delay request, and master will reply with the response. And in this protocol is also known as a two-step, because master will send the two message back to back. Even in this case, the p delay response, and it will be followed by the p delay response follow-up message. Okay, so both the message and the value of the timestamp has been noted down, and both the message are sent by, like, one is from master and the second one is from the slave. So we will have a two propagation delay. So half of this value will be our propagation delay, and the slave then adds this propagation delay to its clock, and hence the clock will be synchronized. Okay. Okay, so there is another logic to find the best master clock is to base master clock algorithm, which is BMCA, which determines the grand master. But today we will not discuss this, and we will skip to the common security threats for the automotive Ethernet network. Okay. So in automotive network, needs arise to protect the data transported on the ECUs, which is electronic control units, and automotive networks are prone to the third-party wiretapping, intrusion, infiltration, and man-in-the-middle, and the playback attacks. And due to this, and these attacks are mostly possible due to the inline connectors and the internet or cloud connectivities. So let's see what are the common security threats. So first is the intruder or the attacker can modify the message that has been transferring between two nodes, or he can send the random messages through the connectors, inline connectors, or they can replay the same messages, recorded messages, or the snoop the data, or the get the data from the node and corrupt it. And the next can be they can exploit these software bugs for future attacks, and they can also install the harmful software or the code, right? Okay. So before finding out or the discussing the solution to uh, this issue, let's discuss the MACsec. So let me introduce the MACsec for a while, and then we will discuss the solution to this common mistakes or common attacks. Okay, so MACsec is stands for the Media Access Control Security, and it is defined in the 802.1a, and it provides the link-to-link security. Okay, so it provides the bidirectional secure link between two devices, and it provides the encryption and protection to the data passing over the ECUs within the vehicles, and it provides a authorized system, right? And it also gives the confidentiality of the data, and we can say it also take the action against the security breach. And to do that, it uses the protocols, encryption protocols such as AES GCM and its various versions like AES GCM 128 and some extended packet number versions as well. Okay. Okay, so this will be the so now we have discussed the PTP, we have discussed the MACsec. So why not use both, like PTP or MACsec? So how the PTP or MACsec frame will look like? So here we can see that the first two fields will be the data. As always, it will be the destination address followed by the source address, and then there will be a MACsec header, right? So MACsec header will contain the ether type value, which will be 88E5, and then there will be a TCI-AN, which is tech control information, which followed by SL and packet number, and then SCI. So SCI is a secure channel identifier, which is optional, and one can be that SCI can be selected from this one of the bit, which is a secure channel bit. If it is enabled, then this extra SCI byte will be added. Then in the data of this Ethernet frame, we will send a PTP frame, which will be completely encrypted by the MACsec. So the first field of this data, I mean within the raw data, there will be a ether type. We will send another ether type, which will be a 88F7 ether type for the PTP frame, and the rest of the data will be the PTP data, and it is secured. Then last two fields are ICV and CRC. Okay. ICV stand for integrity check value, and then there will be a CRC. We all know the CRC. Okay. Okay. So let me zoom out this TCI-AN field. So this TCI-AN field will have few more fields, which is a V for version number, ES, which is end solution, and then SCB, SH, E, and AN, which also follows by the single copy, and then assistant number, association number. Okay. Okay, so this is the overall PTP or MACsec frame format, and okay, so now let's get back to our main point, that why does this PTP or MACsec required in the automotive Ethernet? So as I already discussed, right, that our network is prone to the wiretapping and infiltration, man in middle, playback attacks, blah blah. So it is highly desirable to avoid this kind of disruption or data loss or leakage due to the unauthorized transmission and reception, and it is sensible. We need to protect it, but we cannot protect the entire physical network, right? So it makes sense to just secure the network by the layered security or the link layer security. Okay, so MACsec will add these. I will skip first 2 points, and so MACsec protocol will add the sec tag, which is security tag, ICV, packet numbers, and encryption. And let's see how this will secure this whole automotive network by using a use case. Okay, so suppose a attacker is trying to snoop the data from the connectors, right? And the network is using the MACsec PTP or MACsec frame or the protocols, right? Then frame will have the ICV field, the using which a reception will make sure that the data has not been changed, since this ICV bit, if the man in middle had changed or modified the data, this ICV field will not be the same. So that's how we will confirm the data integrity. We are using the packet number, which will get incremented every time when the new message is being sent. So if someone is trying to replaying the same message over the network, the packet number will not change, and that's how the receiver will get to know that replay message has been sent by the transmitter. Using the security tags, the receiving node ensures that the message has been sent by the authentic link partner, not by the third party. Okay, and the main and the last And the main point is that the communication between two nodes will be encrypted, right? So no one can steal the data or copy the data or the modified. And for that, it uses the AES GCM network. So hence we will get the confidentiality of this network. Okay. So now we will come to this our major focusing part, which is verification challenges for the PTP over MACsec IPs, and we will try to cover the functional verification challenges over here. And I would like to invite the Shubham to discuss that. Yeah, thank you.
Okay, so thank you, Kunal. So in the second part of this presentation, we will discuss about the verification challenges which we may encounter while verifying the PTP over MACsec IPs. So considering the data security and the timing synchronization as a crucial parameter for the automotive Ethernet domain, so we will require a full-fledged verification for such IPs. So very first challenge which we may encounter with this solution, PTP over MACsec, that is the latency may vary due to the MACsec encryption logic. So PTP latency may vary because of the MACsec encryption logic. And the prediction of that variation is very difficult for the verification point of view. Second challenge related to the LAN type issue, because PTP and MACsec both has unique LAN type, and the PTP or MACsec frame will be transmitted over the Ethernet frame, and as Ethernet has only one LAN type field, so as we discussed in the earlier slide, so the MACsec LAN type field will be transmitted over the Ethernet LAN type, and the PTP LAN type will be transmitted in the first 2 bytes of the actual payload. So in this scenario, there could be one case that let's say we are transmitting only MACsec frame, no non-PTP frame. But due to some randomization of the data payload, it could possible that the first 2 bytes of payload may have the exactly same value similar to the PTP LAN type. So in that case, how IP will behave? To cover such scenario, we have to generate the stimulus from our verification environment. There are some more challenges related to the data integrity checks and debuggability because of that encrypted data due to the MACsec, and all types of negative scenario testing, complete coverage closure, verification accuracy, and delay measurements are required for this IP verification. A debugging issue in latency-related scenario on top of the encryption logic may create some challenges. Now we will discuss about some solutions, how we can overcome these verification challenges. So by providing the probes with the complete control of the Ethernet frame at the various level of the IP, so that can provide the help to check the data integrity and debugging of the complex issue. And also we can have some error injection scenario. And second is with the ease of the randomization, we can have the testing of the all possible values of the MACsec keys, MACsec field values, and the as well as PTP field values. And inbuilt a rich set of coverage groups, automatic coverage report generation may make life easy for verification. So let's come to the last slide before the conclusion. So this slide, we have one Ethernet automotive Ethernet IP, and the right-hand side, we have Ethernet verification IP. So in the automotive Ethernet IP, we have PTP and MACsec, so PTP over MACsec, which may transmit over the automotive Ethernet file, that is BST1 file. So for the verification of such IP, we would have the verification IP where there are 5 major parts: configuration, driver, monitor, checkers, and coverage. For the configuration, means to provide the configurability of all possible scenarios to cover with respect to MACsec. It could be MACsec keys, PTP version, because we have lots of many PTP versions. So to cover that, and also to have a configurability to test with the Mac standalone with 5 type of configurations. Driver and BFM is responsible to create the random stimulus to cover all possible test scenarios and also provide the visibility of data and modification capability of data over the subsequent layers of the Ethernet. And then monitor is responsible for the data security, data checking, and also the scoreboarding purposes we can use for the data comparison at the subsequent layer, end-to-end also, and the layer to layer also we can have the scoreboarding using monitor. Checker is the most important part of the verification IP. We should have the extensive list of checker to which helps to provide the easiness in the debuggability of, and also provide the also identify the source of the bug. And the last one is the coverage. So we should have the risk set of cover groups to make sure that we have completed our verification and we have covered all the functional testing. Now, let's move to the conclusion. So with the rapid adaptation of PTP over MACsec in automotive Ethernet, a mature and competent and compliance verification solution for automotive Ethernet helps to reduce time of test and accelerate the verification closure, and also improve the end product quality. Thank you. That's all.
Mr. Shubham Agarwal and Mr. Krunalkumar Patel, thank you for a very interesting presentation. Now, let's open questions and comment from the audience. Do you have any question? Please state your name and affiliation.
Yes, I'm Hiroshi Ota from Toyota Motors. Thank you for your presentation. I would like to ask one question about the time accuracy with MACsec and without MACsec. Do you have any information about or major data about that?
Can you come again?
Do you have any measured data with about time accuracy of ZPTP with MACsec and without MACsec?
No, actually, it's still an open question for us to identify how much latency variation will be there. As long as the variation latency changes is constant, then it's fine. But it should not be the variation in that latency. So we have to measure about how much variation is there. So for that, we can also accommodate the 5 time stamping feature to overcome such things.
Okay, thank you.
Any questions? I see none. Okay, let's move on to the next presentation. Thank you very much.
Thank you. Thank you, everyone.